Alright, so that should fix it. So it should be fixed on YouTube now because I can see the meter is fluctuating. Alright. Alright, so for, I know this is like really kind of bad because we are using two mandatory resources. YouTube is kind of optional, but I can only watch the text going on using Discord because I can't keep my eye on three different things. So, you like YouTube? Oh, okay. Well, we can potentially switch to that too. But YouTube has a lag time that is kind of long. All right. So I still have to keep an eye on Google Meet, just in case some people come a little bit late, like that. All right. Okay. So I think we can get started now. We were talking about values, numbers, and bases. Okay. In other words, how do we represent a value in different bases? So that was kind of where we left off. I was talking about a base conversion example using currency, the U.S. currency as an example, and I was mentioning how since most people can do that, um, they already know how to do base conversion because base conversion is kind of like making change, except the denominations have a very nice consistent multiplier from one to the next available one. So that was kind of the discussion from last time. And I also programmed my OBS to use a hotkey so I can turn on and turn off. Okay, so maybe not. Okay, turn on and turn off the um, tablet. But I forgot to save it, when I got it all set up. And oh, it's not picking up my tablet screen. Okay, that's fine. I'll do it the other way. There we go. All right, so I'm gonna do it this way. So this way it's easier for me to see whether I'm in tablet mode or not. Okay, because a lot of times I forget that I'm. Oh, okay, the tablet mode is actually on. Okay, never mind. Okay, so but it is smaller now, and I need to make it back to the original size. So give me a second here. All right, so make it even just a little bit bigger. There we go. That's too big. There we go. Okay. So we can go back to a previous slide. So this is what we talked about on last Thursday, and I'm hoping all of you had a chance to review the material and also read a little bit ahead of me, because that really kind of makes the class a whole lot easier to absorb in terms of the material. And we even talked about base conversion a little bit because it's just an example of how we converted $18.625 in base 10 to the base 2 representation of the same amount. Okay, so this is what we talked about last week. So what we'll be doing this week, okay, and particularly today, is to talk about base conversion using a kind of weird base, okay? Because base 2 is not weird at all. I mean, base 2 is used a lot in computer science. So we'll basically be talking about how do we do base conversion in general. Section 2 talks about what exactly is a number. A number is a representation of a value. It's kind of like a name, okay? If you think about your name, especially if you have, if you have multiple languages, or if you are in an environment where people refer to you in different languages, so you have different names. Okay, even people with just one single language background, people who are close to you may call you by a certain name, and then people who do not know you as well will call you by a different name, but they're all referring to you. So it's the same thing here. Okay, when we talk about a number, there can be an almost infinite number of ways to refer to a single value. Okay, and in computer science, we only deal with bases that are natural numbers. Actually, I should say counting numbers, because you cannot have a base 0 number. You cannot really have a base 1 number. So base 2 is kind of where we start. So what we do is in section 4, we talk about um, what I call a common base multiple digit number. Basically, the whole idea is to look at this particular value, which is 16.375. So the way we look at this quote-unquote number is we can break it up into 10 plus 6 plus zero point 0.3 plus 0.07 plus 0.005. And you guys go like, yeah, but we know this stuff already. There's nothing special about this, right? And the answer is that you're correct. There's nothing really special about the first line. But then the second line is a little bit more interesting, because on the second line, the 10 is becoming 1 times 10 to the power of 1, and I will get to the text channel stuff in just a little bit. And then we have 6 being 6 times 10 to the power of 0, because 10 to the power of 0 is 1. And then the 0.3 is 3 times 10 to the power of negative 1, and so on. So what the second line is really showing us is when we look at a number, each digit is telling us the quantity of a power of whatever base we're dealing with. Okay, so I'm going to say that one more time. When we look at a number such as 16.375, each digit is telling us the quantity of a particular power of the base of this particular number. In this case, it's a base 10 number. So we're talking about powers of 10. Powers 10 to the power of 1, 10 to the power of 0, negative 1, negative 2, and negative 3 here. And that's why I kind of summarize what is the value being represented by a number. So in this representation, if you read this paragraph carefully, then you would know that D0 is representing digit 0, D1 is digit 1, the negative 1 is digit negative 1. So they are basically positions of a digit. And the value being represented by a particular number in base 10 can now be represented using the sigma notation. So I just go from negative infinity to positive infinity because I don't know the number of digits in a particular number. So I just go like, okay, just go all the way from negative infinity and all the way to positive infinity. Now, obviously, when we write a number, the leading zeros we don't write, right? The trailing zeros we also do not write. So in a practical sense, I is going from usually a fairly small number to a usually fairly small number too. So I just want to pause and see if there are any questions, and I have no idea what is the lag time with Google Meet. So I'll go ahead and let you guys ask questions at this point.
It's about half a second.
So that is very acceptable. Maybe trailing behind Discord just by a fraction of a second, but it's much better compared to YouTube. Okay, very good. Thank you for the feedback. So now let's go ahead and ask questions up to section 4. All right. Oh, frame rate is bad. Okay, yeah. Closed captioning can be good for people who need that for accessibility. But any questions related to the value being represented by a number? Okay, so I'm not seeing any questions related to that. There are 2 direct messages to me, so let me click on those to check what they are. Alright, so there's one. I cannot answer that one right now. Okay, the other one is fine. Okay, so we are back to the text channel. Yeah, go
I
ahead.
just had a quick question.
Yeah, go ahead.
So you kind of mentioned in passing that we can't have a base 1 system. I feel like I kind of get that, but not entirely.
Well,
Like, I
the
get why it can't be base 0.
base 0 you cannot have because 0 to the power of anything is just 0. Now base 1 you can sort of have it, but you have like you basically end up with an infinite number of representations in base 1 to represent a particular value. and that has to do with 1 to the power of whatever is always 1, right? So let's say you want to represent the quantity of 3. You can write 3 in base 1. No, I take it back. You cannot have a base 1 number because in base whatever, you can have digits, from 0 up to that base minus 1. So in base 2, we only have 2 digits, 0 and 1. In base 10, we only have 10 digits, which is from 0 to 9. So in base 1, you don't even have a digit other than 0 itself.
But wouldn't the number of zero, couldn't you just write like 000, and then that would be like 3, and then it's just like the number of.
You cannot, because based on this generalized representation, the digit is specifying the quantity of the power of your base, right? So if all of your di's are zeros, then the sigma is always going to be
I see.
0. Yeah. So you cannot
I
have
see. I see.
you
Okay.
cannot have a base you cannot have a base 1 representation. So base 2 is kind of the lowest base you can start with. All right.
Okay.
Mm-hmm.
Thank you.
Cool. So that was an interesting discussion. Thank you. So moving on, in section 4, this is the last portion of section 4. So this particular expression is really a generalization of this one over here. So the only change is instead of using a constant of 10 as our base, I just generalize that and say, okay, let's just say that we're dealing with base b. Okay, so even the base itself is a variable in this case. But other than that, we are not, there's no change. Okay, so let's go through some examples. Okay, so we are not going through the formal base conversion process, but we are actually just looking at things that seem to be odd. Okay, I like things that are odd, and this is it may be considered odd. So now I just turn on the tablet, and we'll deal with a base 7 number. Okay, so here is an example as a base 7 number. So we'll have 1, 3, 5, and the subscript of 7 indicates that 7 is the base of this number. The only time I do not use a base is when we're dealing with base 10, so it is implicit that a number is in base 10 if I don't specify anything about the base. So when you look at 135, you can then rewrite it as 100 in base 7 plus 30 in base 7 plus 5 in base 7. The 100 becomes 1 times 100 in base 7. The 30 becomes 3 times 10 in base 7. And then the 5 becomes 1 times 1 in base 7. And then what we do, this is really the last step, well, second to the last step, but this is actually the Conical base conversion part, which is looking at 100 in base 7 and go like, well, what is that representing? The number of zeros is telling you what power of 7 we're dealing with. So in this case, we are dealing with 7 to the power of 2 for the 1. We're dealing with 7 to the power of 1 for the 3. And we are dealing with 7 to the power of 0 for the 5. Yes, 0 is 0. So now, everything is now in base 10 because, we are done with base 7, numbers now. So 1 times 7 squared is 49. 3 times 7 to the power of 1 is 21. And then 5 times 1 is really just 5. So when we add up all of these, okay, so each one is representing a quantity times a power of 7 in this case because we're dealing with base 7. So 49 plus 21 is 70. 70 plus 5 is 75. There we go. So it is 75 in base 10. So let me kind of pause here and see if there are any questions about the conversion from 135 as a base 7 number to its base 10 representation, which is 75. Yeah, it's kind of like remapping. It really is boiling down to, let's re-express a value using just quantities of powers of a particular base. And base 2 is well known, base 7 is not. Unless you watch a lot of sci-fi. Alright. So I got some people still typing, so I'm gonna wait a little bit here. And I'm gonna heptapod. There we go. I remember looking it up at one point. So a heptapod is a creature that has 7 limbs. So you would kind of imagine that those creatures would use base 7 because we use base 10 only because we get 10 digits, right? 10 fingers. So a heptapod is very likely to use a base 7, system. And yes, by the way, it is a great movie, and no, the movie does not actually explain base conversion. It explains something that is far more, sci-fi-ish. But anyway, base 7, there's no reason why, creatures, cannot use base 7 or base 5 or base 11, okay, or base 15, there's no reason why those bases cannot be used, okay? We use base 10 and base 10 is really not really a nice base to use anyway. So, all right, so we got one question related to the question. So 100 in base 7 is 1 times 7 to the power of 2 plus, yes, that is correct. So Andrew is correct. Oh, base 16 is easy, okay? Yeah, because the conversion between bases is nasty. Unless you're dealing with a source base and a destination base where one is a power of the other one. So 16 is a power of 2 because 2 to the power of 4 is 16. That makes the conversion from base 2 to base 16 and the other way around very, very easy. Okay, because from base 2 to base 10 is kind of a chore. It's not impossible, but it is a chore. From base 16 to base 10, yeah, kind of the same thing. From base 10 to base 16, kind of the same thing. But when you're talking about from base 2 to base 16, it's like super easy. And then from base 16 back to base 2, super easy too. So we'll get to base 16 at some point because, when you're dealing with base 2 numbers, okay, one of the bad things about base 2 is you need more digits to represent a particular quantity. So to deal with that problem, we instead of using base 2, we use base 16 because you only use 1/4 of the digits when you convert a base 2 value or base 2 number representing a value to base 16. The required digits will be only 1/4 of the base 2 representation. Yeah, so you can kind of look at it as a remap of base 2. Now, since we are on this topic, instead of deferring this topic until a little bit later, which is kind of the usual thing that I do for this class, but since we're on this topic, I might as well talk about it. Okay, so this is a good time to really kind of introduce base 2 and base 16 and how they convert to each other. Okay, so we'll go ahead and let me turn on the tablet again, and I have a hotkey to do it now. It's Alt R, R for remarkable. So we'll go ahead and look at the conversion process. So we'll go ahead and take a look at let's see. So I'm going to look at a hexadecimal number. So C as a programming language already has the provision to specify values using hexadecimal, and 0x is the prefix that you need in order to tell the compiler what follows is a base 16 number. So you might be asking, well, but in base 16, aren't we going to run out of available digits because base 10 has got 0 to 9, so base 16 need to have 6 more digits. And the reason why it is okay is because we borrow letters from the alphabet. So let me read some of the questions in the text channel first. Okay, so let's start with the first one. 7 to the power of 2 represents the hundredths place because I relate the 2 as 2 zeros. And 7 times 1, 7 to the power of 1 represents the 10th place because, right, so the position of a digit is correlating with the power, the, the, the base to which power is that digit representing. So this all kind of goes back to the sigma notation that I have already included in the notes here. So this is the sigma notation. Let me turn off the uh, tablet for the time being. So this is the formula that I'm talking about, where d subscript I is representing digit I, and these digits can go negative too. Okay, but the position being negative simply means it is to the right hand side of the point. Okay, remember from the last discussion on Thursday that the point is nothing more than a separator. It is only a marker to basically say where is the digit for the base to the power of 0. That is what the point really is doing. It is basically saying, whatever digit is immediately to the left hand side of the point is the digit for the base to the power of 0. So whatever is to the right hand side of the point would be quantities, would be digits specifying the quantity of the base to some negative powers. So in that case, it would be, I having a negative value. And then on the left hand side, we have all the positive powers of the base. Okay. So I hope that is answering some of the questions. I'm not sure whether this is answering Rachel's question. The base 10 representation all the way up here, the example using base 10, that the intention of this part here is to break down a number that we are very familiar with, basically it's a base 10 number, and explain what each digit is doing. Each digit is specifying the quantity of a power of the base that we are assuming in this case, okay, because we're assuming base 10 when we don't specify, when we don't spell out this is a base 10 number. We got a few more people typing, so I'm gonna take a pause here while I work on an example here. Okay. Alright, so I can show a conversion between base and something else. Okay, I can certainly do that. Alright, so, okay, we can do something visual. That's fine, not a problem. But I want to, let me think about, how to do this. Let me turn on the tablet first, and then, we'll go ahead and do one visual conversion. How about that? Okay, so let's do a visual conversion. So we'll say the value that we want to convert. So this time we're doing quote unquote base 10 back to base 7 conversion. Okay, so the value that we want to represent. Okay, I got one person trying to join us now. I'm gonna admit that person. There we go. So I'm going to use an example. We'll specify a value of something that we are familiar with. So let's say 120. Okay, so we're starting with a value of 120, or what we know as 120, which is a base 10 representation of that quantity. Okay, and I'm just going through the text here. Yeah, so the whole idea is when we go through this example, I think you guys would get the idea, okay? And I'm looking at Luke's comment on Discord. D can have a value from 0. D is the actual digit, so it can go from 0 to b minus 1. That is correct. So when we're dealing with base 2, which means b is 2, then we only have 0 and 1 as available digits. When we're dealing with base 10, which is the base that we are familiar with, then we have 0 to 9. That is correct. So what Luke is saying is correct. All right, so let's go ahead and convert 120. So let's focus on the tablet. So we are looking at 120 as a quantity, and we want to convert it into base. Let me see. Base 7. Okay, so we're going to go back to base 7 here. So now we look at base 7. And we know in base 7 there's one digit corresponding to the quantity of 1. There's 1 corresponding to the quantity of 7s, 1 for quantities of 49, and we know 49 is going to be okay because 7 times 49 is way bigger than 120 to begin with. So we know that these are the powers of 7 that we need to deal with. So what we do is we divide 120 by 49. We got 2 of those, right? So we say there are 2 49s. So after 2 49s, then how much do we have left? Okay, I shouldn't write it here. So we say 120 minus, that would be 98, right? So we have 22 left. So when we have 22 left, and the only remaining digits that we have would be to specify the quantities of 7 and 1. So when we look at 22 and ask how many 7s would fit into 22, then the answer is 3, right? So there are 3 7 to make up 21 for the 22. Then we look at 22 and say, okay, of 22, 21 is already taken care of. So the last digit only has to deal with the quantity of 1. So that means we just need a 1 here. So now we have this as a base 7 number. 231 as a base 7 number is representing the same quantity as what we know as 120. So is that kind of helping the process? Oh, okay. All right. So let's go back to currency because because this is the part that is really amazing, is how we can do something that has no regularity, but because we do it on a daily basis, we know how to do it, and we do it very comfortably. And then when we deal with something that is that has regularity, but because we don't actually do it on a daily basis, it feels foreign to us, or I should say alien to us, right? Okay, so let's go ahead and look at the same quantity, okay? 120, but this time it is $120, okay? And we want to use the least number of bills and coins to represent 120. And everybody knows that, oh, tech, this is easy peasy, okay? We just need 12,000 pennies, and that should should do it. No, right? I mean that's not a good answer. Okay, using 12,000 pennies to get to $120 is an awful solution. But you guys already know the answer, right? It's like one $100 bill and one $20 bill. That's all we need. Well, that's because when we're dealing with currency, we are dealing with something that looks like this. Let me turn the tablet's on already. So we are dealing with a penny, which is 0.01, a nickel, and dime, quarter, dollar, $5 bills, $10 bills, $20 bills, $50 bills, and $100 bills. Okay, that is what we are dealing with when we're dealing with currency, U.S. currency. Okay, so how do you know how to make a change, right? If I specify something that looks a little bit more challenging, let's say $168, how do we deal with that? So we look at 168 and we look at the currencies that we can deal with, okay, which are these specific values over here, and we say, yep, we need one of these. Okay, so once we use a $100 bill, we only got $68 left. Okay, let me take a look at the. Okay, so there's a whole bunch of text channel stuff going on that is not exactly synchronized with what I'm talking about. So if you for the rest of you, you can focus on me and then go read the text channel stuff later. I will go back to the text channel stuff. It is still good stuff. It's just not synchronized with what I'm talking about at this point. So when we look at 168, we only got 68 left. So of the 68 left, the next available currency denomination is 50. So we say, hey, there's 150 in 68. Okay, we can take one of these. So now we have taken care of 150 out of 168, which means we have 13 left. So out of the 13 left, we say, nope, we are not going to need any 20, but we'll need 110. Okay. So of the 18 left, okay, 10 is taken care of, which means we now only have 8 left. So of the 8 left, we need 1 5 and 3 1s. Okay, that is what we are doing with base conversion. Except in base conversion, the multiplier between the denominations is no longer kind of random like currency. It is a constant. Okay, if we are dealing with a very odd base like base 7, then they're all um, powers of 7. Okay, if you're dealing with 5, they're all powers of 5. If we are dealing with binary numbers, they're all powers of 2. That really is the trick, to use what we already know about currency, how to make change, and use that knowledge and transition to base conversion. So I'm hoping this kind of help out people who are um, a little bit uncomfortable with base 7. Okay, because base 7 is really odd. Okay, because we can think about base 5, that seems to make sense, and we can think about base 10, that kind of makes sense. Even base 2 makes more sense, but base 7 is not any more odd, well, in this case prime, than any other base. So let me check out what is going on in the text channel. There's a lot of stuff going on here. There's some discussion of hexadecimal, which I'll get back to. Yes, we are going to have a lab today. You can count on it. I don't even know why that question is asked. Yes, we do have a lab. All right. So, oh, by the way, just as a joke, there's also a good reason why base 7 makes a lot of sense, and it's going to be used by octopi, like the plural of octopus. And you guys would say, but Tech, don't you know that octo means 8? I know. But what if the octopus needs 1 tentacle to hold a beer and only has 7 tentacles left for counting? Yes.
Dr. Tack.
Yes.
How would you do an? No, I guess you. How would you do an? Such a. Could you do 2? No, you can't go lower than 7 in base 10, could you?
Say that one more time.
Could you go lower than 7 in base 10?
Can I go lower than 7 in base 10?
Or sorry, base 7.
Base 7. So to represent 7 in base 7, it is going to look like 1 0. Because 7 is 7 to the power of 1. So that's why we have to specify we have 1 of 7 to the power of 1 and 0 of 7 to the power of 0.
And we're allowed to use all digits between 0 and 7, including 0 and 7?
You can only use 0 to 6 as available digits when you're dealing with a base 7 number.
Okay.
Yeah. Yeah, it's just like, we don't have a single digit in base 10 to represent the quantity of 10. Does it make sense? Okay. So I'm going through the text channel here.
Could I ask a quick question?
Yeah, go ahead.
Can you have an irrational number as a base? Could you have like e or pi?
There's no reason why you cannot, okay? Because you're still using the sigma, the summation. So if I go back, let me turn off the tablet for the time being and go back to the notes, okay? So if you look at the notes here, there's no reason why b cannot be a irrational number. So if b is an irrational number, just to specify an integer, it's going to take an infinite number of digits, right? Because it's exactly the reverse of the problem that, if b itself is an integer, a positive integer, then it would take an infinite number of digits to specify a irrational number. But, yes, you can. I mean, there's no reason why b has to be an integer. It can be an irrational number, and you will still be able to specify a value based on, just the quantity of the power of each power of the irrational number. So it is still doable. Okay, I'm pretty sure some mathematician is working this out and go like, yeah, this is kind of cool. I don't see any
Yeah.
application in computer science, but yes, it can you can choose B to be anything. I think as long as it is well, your D
Applicable
is going to
enough.
be your D is going to be funny, right? Because if B is irrational, then what can you use as the range of D, right? So you might need to make D also irrational too, in that case.
Hmm.
So if B is
Okay.
irrational, then the D's of I would also have to be irrational. It has to be from 0 up to, but excluding the base itself. So
I see.
let's kind of shelve that discussion, even though it is
Sure, sure.
theoretically kind of interesting. All right. So let's go through some more examples, okay? Because I think more examples is going to help out in this case. So we're going to use, 0x2dc as an example. So let's see if that is going to help us, gain a better understanding. So I'm
You
switching back to the tablet now. Go ahead.
so you converted one into base into base 7, right? So how do you now, like, we figured out it takes two 49s, three 7s, and one 1s.
Yeah.
How do you represent that
Oh, okay.
as an answer?
Well, the answer is right here. As a base 7 number, 231 is representing what we know as 120.
Oh, okay. Okay. Thank you.
Sure. All right, so let's go to a new slide here, which starts with a hexadecimal number. So the first part, which is 0x, is merely a prefix. Okay, so don't ask me why it is 0x. It is a prefix chosen by, I guess, the originator of C, to mean that, okay, whatever follows is a hexadecimal number. So when we deal with hexadecimal number, we kind of have to, it's in the text description, in the text discussion already, but we're gonna take a look at the available digits. Okay. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, coming from the base 10 digits that we are familiar with. Okay. So 0 just means 0, none of, right? 1 means 1 of, 2 means 2 of, and so on and so forth. Okay. But then we run out of digits because we only got 10 digits in base 10. So what we do is we borrow letters from the alphabet. Okay. And because computer science, at the time at least, is mostly a American slash British thing, so they borrow these letters from the English alphabet. Okay, so that's the only reason why we have A to F and not alpha, beta, delta, and so on and so forth. Okay, or alphabets from a different language. Okay, so but we do have we just use A to F. So when you look at A, it really means what we know as 10. B is what we know as 11, 12, 13, 14, and here's 15. So when we look at 2DC as a hexadecimal number, that means we have C times 16 to the power of 0. We have D times 16 to the power of 1. And then we have 2 times 16 to the power of 2. So the 16 is because that is the base. Hexadecimal, is hexa, which is 6, and then deci, which is 10. So hexadeci added together is 16. So we're dealing with base 16. So now we're trying to specify how many 16 to the power of zeros do we have, how many 16 to the power of 1, and how many 16 to the power of 2. So this one is easy, right? 2 times 16 to the power of 2 is 512. Because 16 to the power, oh, I take it back. Nope, this is right. Okay, so this is 512 because 16 squared is 256. And then we have 16 to the power of 1, which is really just 16. But then we look at this digit here and go like, wait, hold on a second here. What is a letter doing here in a hexadecimal number? And then we remember, oh, look it up over here. D is representing the quantity of what we know as 13. So this is really just 13 times what we know as 13 in base 10 times 16. And 13 times 16 is what? Yes, I am terrible when it comes to arithmetic, so I gotta spell this out. I cannot do mental math like some people can. All right, so we are looking at 208. Looks right to me. All right, and then what is left? So we got the C is so if you want to look at this, there's an implicit point here, right? Because C is the least significant digit. So unless we have decimal numbers, the least significant digit is always specifying the quantity of the base to the power of 0. Okay. So now we have 12 times 16, and 12 times 16 is, oh, that one is easy. I think that's, oh, no, I take it back. 12 times 16 to the power of 0. I forgot about it to the power of 0. 16 to the power of 0 is just 1, so 12 times 1 is just 12. So now we add up all three, and, alright, yes, I have to admit that my arithmetic is awful. So we have 220 here, so we got 732. Is that right? Well, we can always do a conversion back, okay? That's the beauty of this whole thing, okay? I'm going to do a conversion back, but this time I'm going to convert it back to base 2. All right? So let's just say that, some of you are thinking, Tech, you might have made a mistake, but how would we know that you have just made a mistake? Right? So we're going to convert this number back to base 2, and then we'll take a look at the conversion between base 16 and base 2, and then that will help us check to see if at least things are consistent or not. Now, there's an odd chance that I can make very, very consistent mistakes somewhere so that the whole thing works out even though there are mistakes in it, okay? But it's very unlikely. So we're going to convert the whole thing back to base 2 now. Not base 16, base 2. So we look at 732, which is a base 10 number, and then we will try to convert it into base 2. So when you're converting into a particular base, at least from the beginning when you're starting out, it really helps out to spell out all the powers of that base first. And then you just ask yourself, how many of these do we need? How many of these do we need? And how many of these do we need? Okay, so that's a very visual process. So now I'm going to write out all the powers of 2. Well, all the ones that I think would be useful. So we have 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. I think that's more than what we need, right? Because the value that we want to represent is 732. So we kind of know that 1024 is already too much. All right, so I'm looking at the text channel here. Yeah, except the 0x is a little confusing from Grant, but otherwise, that is correct. Okay, that's the way we figure out what value is being represented by 2DC as a base 16 number. Right, that is exactly right. Okay. All right, so now we are looking at the base conversion from 732 back to base 2. So we say, nope, we are not going to need any 1024. We'll take 512. Okay, so on the side, because my arithmetic is really bad, so I'm going to do this calculation on the side. So now we have 220 left. Now with 220, I don't need a single 256, right? So we say there's none of those, but we need one of 128. So we say, well, let's subtract that and find out what is left. So there's a 2, there's a 9, so we have 92 left. With 92 left, we say, well, we need 164. So now we take 64 away from 92, and we have 28 left. So with 28 left, we don't need a 32. we're going to take a 16. Okay, so we subtract the 16 from the 28. We have 12 left. So with the 12 left, we're going to take 1 8. And once we take the 8 out, we have a 4 left. So we say we're going to need a 4. And then we have 0 left. But we're not going to stop here. Okay, we got to work out everything, right? So with 0 left, I ask myself, do I need a 2? No. With 0 left, do I need a 1? No. Well, now we have a representation of the quantities of powers of 2 that we need in order for all those quantities of powers of 2 to add up to 732 in this case. Yes, so b to the power of n, where n is the position, is the key, because that's the denomination. Okay, that really is equivalent to denomination. The $100 bill, the $50 bill, the $20 bill, the $10 bill, the $5 bill, and so on. Except in this case, they're very regular. Okay, they're all multiples, a fixed multiple of each other. All right, this is good. Okay, but we still have to answer the question: Did tech make a mistake in this whole conversion thingy? Right. So what if I tell you that the conversion between base 16 and base 2 is nothing more than a table lookup? Okay, and I'm going to make the table here. If you want to capture this, at some point and kind of just copy and paste it into your own notes, that's fine. If you want to make this look really nice using a spreadsheet, that's fine too. But I'm going to make a table, very small table here. So what we do is we look at hexadecimal digits. I use hex as an abbreviation instead of spelling out hexadecimal. So hex means hexadecimal in this case: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Okay, and then I use bin to represent binary. So this is the most important part. Every digit in base 16 is representing 4 digits in base 2. Let me say that one more time. Every digit in base 16 is representing 4 digits in base 2, and that's kind of makes sense in a way, because 2 to the power of 4 is 16. That is why. Okay, so we now look at 0 and ask what represents 0 using only 4 bits. That's easy. Here's 1, right? Here is 2. Oops, I just made a mistake. A little bit. Okay, that's 2. This is 3. Oops. 4 is 0, 1, 0, 0. 5 is 0, 1, 0, 1. 6 is 0, 1, 1, 0. 7 is 0, 1, 1, 1. 8 is 8 is 1, 0, 0, 0. 9 is 1, 0, 0, 1. A, which is the same as what we know as 10, is 1, 0, 1, 0. And then 1, 0, 1, 1 for B, 1, 1, 0, 0 for C, 1, 1, 0, 1 for D, and then 1, 1, 1, 0 for E, and then F is 1, 1, 1, 1. Alright, so yes, I know this is horrible the way I wrote this table, and Jonathan did a much better job with this table. Thank you. Okay, and you can probably look this up on Google. Yeah, and there are very nice tables out there. Okay, except you don't need this table for very long. Okay, after one semester doing this kind of base conversion, by the end of this semester you will say, I don't need no stinking table for this kind of conversion. Okay. All right, so what does this mean? Okay, so what this means is, in order to convert between base 16 and base 2, we just have to look at chunks of 4 base 2 as one equivalent base 16. That's what we're going to do. So you have to remember that we should start with the least significant bit. Okay, which means we're looking at bit 0, and then from that end we chop into chunks of 4. So in this case we got this chunk of 4, and then we got this chunk of 4, and then we got this chunk of 3. What are we going to do here? Well, it is always okay to pad additional zeros that usually we don't need, because we don't want to write unnecessary digits. But when you're converting from base 2 to base 16, it's always good to pad additional zeros to the left hand side so that we have a multiple of 4 when we are counting the number of digits in base 2. Okay, so now we then we use a table lookup at this point. We look up what is 1100 in the table lookup, and this time we're looking from bin back to hex, right? So we look it up and we say, hey, 1100 is a C, so that's a C in hexadecimal. And then we look up 1101, okay, this is the next chunk, and we look up the table. 1101 is down here. It's represented by D in hexadecimal. And then we have 0010. We look up the table. 10010 is represented by a 2, and guess what? We got our 2DC back. Okay, now does that mean the tag is absolutely correct in this entire conversion process? Well, there's still a very slight chance that I might have might have made a mistake somewhere, but it is very unlikely. Okay, it's just very, very unlikely. Yes, you can spell out all kinds of fun stuff using hexadecimal. My favorite, because this class is usually taught, at a dinner time, my favorite is this. I'm not sure. Oh, okay, you guys are getting it. Very good. Yes, so there. Yes, you can also do something like this. There you go. Yeah, well, I mean, yeah, it's geeky, right? But that's what this class is all about. So are we doing okay so far with base conversion? Cool, cool. And I'm just looking. We got 2 more people typing in Discord. I'm just gonna wait a little bit there. All right. So we have a question. Are we going to add, subtract binary numbers today? Nope, not today. So what we'll do today is to look at some equations. So we're going to say, how do we convert a value, v, some kind of value, to some base b? In other words, I give you the value, usually specified in base 10, and then I say, well, what is this number going to look like in a particular base b? Okay. So okay, I got the tablet on, didn't I? So the question is, okay, this is the question. Okay, if I tell you what a value is in base 10, and I ask you to convert it into base b, whatever b is, how do you go about doing that, right? I mean, well, one way to do it is to use the method that I have described in the tablet. So let me turn the tablet back on and go back to the page, okay? So the way we do it is like this, okay? We just spell out all of the powers of a particular base, and then we use division and subtraction and stuff like that to figure out, oh, we need 1 of these, 2 of those, 0 of that, and so on and so forth, okay? Yes, you can do it that way. I think that's a very intuitive way of doing things, but it is not one way, it's not a way where you can say, oh, I know how to program that in, okay? Because, the whole idea is we want a method so that, it's systematic, so that we can convert it into an algorithm, and perhaps even to specify the logic in C or C++, so that we can have the computer to do all of this kind of chore stuff, okay? Because we don't like to do the chore stuff. We want to leave that to the computer to do. So the bottom line is we have this generalized equation down here, where di is the same thing. It is digit I. Okay, so what should digit I be? and then we have v being the value being converted, and then b is the base.
The
And
tablet's still there.
oh, sorry about that. I keep forgetting that. There we go. Okay. So this is the portion. This is the equation that I'm quoting. So d of I is digit I, and remember I can be positive, it can also be negative. When I is negative, it simply means it is a digit to the right hand side of the point. Okay, and I can illustrate an example of how this works too. But for the time being, I'm just explaining this general equation. So we have v divided by b to the power of I, okay, and b is the base, and then this funky looking symbol here, it looks like a square bracket, but somebody is forgetting the top part of the square bracket. That's the floor symbol. Okay, it is taking the floor of this division, and then mod b. Okay, mod is modulus. Okay, which is also known as taking the remainder after a division. All right, so we look at this equation, and then let me see what happens when I turn the tablet back on. I think the tablet does not cover the expression. Let me just check. Yeah, just barely, not touching it. Okay, very good. So what we'll do now is, okay, let's plug numbers back into this general equation and see whether it works or not. Okay, because we want to kind of try these things out. We start off with an intuitive way, which is spelling out every single power of a particular base, and then we manually, okay, using division and subtraction and stuff like that, figure out what is the quantity of each power of that base we need. Okay, but it is not easy to convert that into a program. This looks kind of nicer, right? Not necessarily. Okay, so the question is, does floor mean round down? For non-negative values, yes. But for negative values, it is not. So floor is rounding. Oh, I take it back. Yes, it is just rounding down, even for negative values. Because the floor of something is the largest integer that is less than or equal to that something. So floor is always rounding down. Even when the value is negative, you're still rounding down. And ceiling is rounding up. That is correct. And I wouldn't even call it rounding. Alright, so let me give you some examples of floor. This is easy. Okay, what is the largest integer that is less than or equal to 1? It's going to be 1 itself. Okay, fine. What about the floor of 1.5? In other words, what is the largest integer that is less than or equal to 1.5? Well, that's also 1, right? So now we will play with some negative values. What about negative 0.5? So what I'm asking is, what is the largest integer that is less than or equal to negative 0.5? The answer is negative 1. All right, so that's kind of what floor does. Okay, it is so the floor of x is the largest integer that is less than or equal to x. All right, but since we're not going to deal with negative v here, because the sign, we can take care of the sign in a different way, so we're not going to deal with any negative v, so we don't have to take into consideration that. So it's so floor is sort of just taking the integer part of a particular value. All right, so we'll check this out. Okay, does it work? So now we're gonna plug values back in. Oh, okay. Yeah, floor and ceiling are actual math functions. All right, so what we'll do is we are going to use this slide here, okay, and we'll do some conversion. So we're going to say, what is the base? Okay, let's pick base 16, and we'll now say, what about I? Okay, which digit are we talking about? And we'll pick 1, okay, and then we'll say, what about V? let's pick the one that we are dealing with, which is 732. So we have been working with this particular value, for the past, half an hour at least. So we're going to use, 732, and we'll try to figure out what is digit 1 in base 16 representation. So that's what we're going to do. And yeah, there's a lot of stuff in 440. 440 is a kind of funky class. It depends on which college you're taking 440 from. If you're taking 440 from ARC, the topics are a little bit different from the other colleges because we have updated ours to match the CID template, and some of our sister colleges, hasn't done that yet. So that's kind of, it's an issue, to say the least. All right, so getting back to our example, let's figure out what is the digit. So we're looking at digit 1, and digit 1, according to the equation, is the floor of the value, which is 732 in this case, divided by the base, which is 16 to the power of the position of the digit, which is 1, and then the whole thing mod whatever the base is, which is 16 in this case. So mod is known as the percent symbol in C and C++, just so that you can correlate between what I call mod here and the percent operator in C. So we'll do this conversion. So we'll say, what is 732 divided by 16? So we got, let's see, 5 would be too much, so we got 4 of those. So we have 64, and then we have a 92 left. So we have 5, 6 would be too much, so we only got 5 here. So that's 80. So 45 with a remainder of, 12, right? There we go. But we only want the 45 point something, right? So this becomes 45, and we have a mod 16. So 45 divided by 16, what is, basically we're asking what is the remainder of that, right? So 45 divided by 16 is 2 with a remainder of 13. So this is 13. But remember, 13 is a base 10 digit. Since we're converting into base 16, we don't specify the quantity of 13 as 13, we specify that as D. So that is D in base 16. Well, guess what? That is correct. That's what the D is. Yeah.
Why is it 13? Because you got remaining 12.
Because 45 divided by 16 is 2 with a remainder of 13. Because mod is the remainder after division.
Oh, okay.
There we go. So it does work. Cool. All right. So now we move on. We are almost done with this entire module. What about binary numbers? Well, guess what? Once we know how to deal with base 7 numbers, we know how to deal with base 2 numbers, right? Because all we have to say is, haha, B is 2. That's it, right? I mean, there's nothing else to say. But there's one really nice thing about binary numbers. Okay, with all of the other bases, I guess my tablet is still on. So with all of the other bases, you need division. Okay, because in order, let me turn the tablet back on because I need that example. Let me go back to a slide here. Right. So with base 7, this is the example that we used in base 7. So with base 7, in order to figure out that we have 2 of 7 to the power of 2, we need that division because 120 divided by 49 is 2 point something, and we just need the 2 out of that 2 point something. So we need division. And then we need to track what is left, which is basically the remainder, and so on. So it involves division. But when we're dealing with base 2, there is no division. There's only comparison. Okay, we just have to do a compare. If it is greater than or equal to, then we got that particular power of 2. If not, then we have 0 of that. In other words, it is only a matter of presence versus absence. Okay, do we or do we not have this power of 2? So that makes conversion to base 2 a little bit easier compared to the conversion to other bases because there's no actual division involved. Okay, but if you don't want to, but it's not. It's a special case in the sense that it is easier, but you can always use the equation that I have shown here to convert a value into its base 2 representation. All right, so are there any questions about all of this kind of base conversion thing? From base 10, which is what we are familiar with, to some random base, and then from some random base back into base 10. Are there any questions? I'm looking at the text channel right now. Oh, okay, I have been missing some discussion about the CID. All right.
I've got a quick question.
Mm-hmm.
So I just want to clarify, or just want to make sure I understand. You said that equation is only for converting to base 2, right?
No, I did not say that. You mean this equation here?
Yes.
It's for any base B.
Any base B. Okay, got it.
Yeah, so B can be 2, 3, 4, and so on. So it has to be an integer greater than or equal to 2. But this equation will work for any base.
Gotcha.
All right,
Thank
cool.
you.
And then we got some text stuff going on in Discord. Let me answer those questions now. So getting back to Omer's question, so is this telling us that 13 is the base 16 value of 732? The answer is no. Okay, so let's go back to the notation. Okay, where's my notation? There we go. So we are looking at B being 16, so we're dealing with base 16. We're looking at I being 1, which means we're looking at digit 1. That is the position of a single digit in this conversion. Okay, and the value is 732. So 13 is one digit. It is digit 1 in base 16 in order to express 732. So there's that. And Andy just answered that question, so very good. Thank you. And so did Rachel. Very good. All right, you guys are getting it. Cool. All right. Any other questions? Doesn't it feel good, when something finally clicks? It's kind of like the eureka moment. How do you do B sub naught? Well, you tell me, right? I is 0, so you just figure it out. This core does not support subscripts. Probably not. You can just say D0 in that case. Yeah, but this chord looks at the underscore, with a special meaning, for underline. So if you use 2 underscores to surround something, it's going to underline that something. And I did not bother to turn on MathBot on this particular server. MathBot would be able to express subscripts and stuff like that. All right. There's a way to do it, Andrew. There's a way for Discord to render LaTeX. I just have to point MathBot to this server, and then it will be able to do it. I did it for CISP310, but not this class. Yeah, it is very sick indeed. And that's why I like Discord. It's got all kinds of bots. I have written a very simple bot myself, I have to say. It's embarrassingly simple, but nonetheless, it does talk to Discord, the server, and it's kind of cool. It's cool from the perspective that I know the API and how to talk to the Discord server. Yeah, I think so. And they're hiring too, if anyone is interested. All right. So, any other questions related to base conversion? Okay, and we're going to move on and talk about section 7. So, section 7 is basically saying, how are values represented in a computer? Well, we already know that inside a computer, they're all quote-unquote transistors, and we only care about two states, when we are talking about the voltage, coming out of a particular lead or copper, on the motherboard or, inside the chip. It's basically, is it representing 0, which means the voltage is below a certain threshold, or is it representing a 1 because the voltage is higher than a particular threshold? So that means inside a computer, everything is represented in zeros and ones, or what we know as zeros and ones. Inside the computer, obviously, it is either a voltage below a threshold or a voltage, above a particular threshold. So everything is base 2. Then you guys will be asking, but then how can we be possibly writing programs and specifying constants in base 10? Well, the answer is very simple. The compiler has been doing the base conversion for you all this time, okay? So the computer does not, does not natively understand base 10, not even close, okay? Every single time you enter something in base 10, the computer actually has to go through the conversion process to find out, what are you talking about, okay? What are you talking about, like 23, what are you talking about? The computer actually needs to parse the string 23 and then convert that into the base 2 representation of 23, which is 10111. Yes, that's what I said. 23 in base 10 is 10111 in base 2. Let's do a quick exercise, shall we? Okay, so let's go ahead and do it. So 23 in base 10, TAC claims this is 10111 in base 2. Okay, and I did all the calculations in my head, but that's because I've been dealing with this stuff for a long time, okay, and I can still make mistakes. So let's check to see if that makes sense or not, because I want you guys to have a chance to exercise what you have just learned in today's class. So we look at 10111 and we ask, what does that mean as a base 2 number? So we write out the powers of 2 again. 1, 2, 4, 8, 16, and that should be enough because we only got 5 digits, so they will be digit 0 to digit 4. This guy here is digit 0, okay? It's digit 0 because it specifies the quantity of the base to the power of 0, okay? So when you're doing the lab today, keep that in mind, okay? Digit 0 is the least significant digit. All right, so we look at this and go like, okay, according to the base 2 number, we have one of these, none of that, one of these, one of these, one of these. So when you add up, you're basically saying, we got 16 plus 4 plus 2 plus 1. So that's 20 plus 3, and indeed, it specifies what we know as 23 in base 10. All right. And so the computer has to go through all of this stuff here, okay? When you type 23, as a constant in your program, the compiler is looking at 2 as an ASCII code, 3 as an ASCII code, and it has to go through the conversion process to convert it into the internal representation, which is 10111, which is a part of a 32 or 64-bit integer. But all that means is you just have a whole bunch of zeros to the left-hand side. So you just have a whole bunch of zeros here to make up for the width of the integer. All right, so now we're moving on to section 8. So in assembly, we are working directly at the lowest level, blah, blah, blah. Okay, so you are correct in a sense, but the fact that we are using assembly language means that we are not really quite at the lowest possible level. Because assembly language is already a language, which means the computer is doing some work to alleviate the whole effort of programming a computer. So let me do two things. Okay, so we'll finish this particular module by mentioning number 8, which is writing a C program to do base conversion. I mean, this is not a graded assignment, so if you want to do this in Java, fine. If you want to do this in JavaScript, fine, and so on. But don't try to do a conversion between bases that we are very familiar with. Okay, so try to write a program to convert from base 10 to base 7, for instance. Okay, that makes it a little bit more interesting because otherwise, a lot of programming languages, can specify base 2 as an output or base 16 as an output, without you having to do any work. Okay, so base 7 would be a kind of really interesting base where the computer or the compiler does not have a built-in capability to do that. So that's going to be, you know, I'll let you guys think about this. Okay, it's not an assignment, but I'll let you think about it, and then on Thursday, I'll give you a solution. There are plenty of solutions out there, but I'll give you a solution. And I'll probably give you a recursive solution on Thursday, just so that it's kind of fun to work on. Okay, so that is that. And then we are going to work on the lab today because somebody asked, are we going to have lab tonight? Of course we're going to have lab tonight. Otherwise, it wouldn't show up on the schedule. Alright, so the base that we have tonight is for base conversion. And let's see here. Recursion. Yeah, go ahead.
Whiteboard.
Oh, whiteboard. Thank you. Control. There we go. Alt R. So this is about base conversion, and the key is octopus. Remember that, octopus with a can of beer on one tentacle? Yeah, I can see that in SpongeBob. What is the name of that octopus in SpongeBob?
Squidward.
Yep. So I don't think I've ever seen Squidward with a beer. And squid, do squids have 8 tentacles?
It depends if it's male or female and how long it gets. It's more varied than octopuses.
Ah, I see. Alright, so we're gonna give you, today is the 26th, and 10 p.m. is the due date. Because this really is a lab, okay? It's not a homework. Yeah, it's not like a homework assignment where you can do it. Oh, I will do it anytime I want. No, this is a lab. Okay, so you have to do it within the time frame. But I don't think it will take you guys even close to an hour to get this done. Okay, as soon as you understand what the questions is asking, it should not take that long. So I'm gonna.
What is the name of the lab?
The name of the lab is base conversion, I think. And then the key is octopus. Yeah, so this is the name of the lab. It is just lab : base conversion, and then the passcode is octopus lowercase. It should be open now. If you guys kind of refresh your browser, you should be able to see the base conversion lab, and then if you click on it, it will ask you for the passcode, and the passcode is octopus. All right. Oh yeah, octopi can actually open jars and stuff like that. Somebody conducted an experiment. I believe it was in Italy. So they captured two, or they didn't capture. They bought 2 octopi from a fish market. So these octopi were about to be cooked to begin with. So they bought 2 octopi, put it into 2 different aquariums where they are visible from each other, and then they put a crab, food for octopus in a jar, and then and close the lid. It's a twist type of a lid, and they put it into the 2 aquariums. One particular octopus, for whatever strange reason, knows how to open the jar. But when it was opening the jar, the other octopus who can see the one who can open the jar was trying to figure out, okay, how did you open that? How did you open that, right? And then the one who knew how to open the jar, was using its back to face the other one. It's like saying, I'm not going to show you. This is a secret. I'm not going to show you. But the other octopus, actually eventually figure out, from just the motion of the one who knew how to open the jar, and it learned how to open a jar to get to the crab inside the jar. That was kind of interesting. Nope, squids are not octopus. Neither are cuttlefish. And they all taste differently too. Yep, I know. Horrible. Horrible.
Fry any of them correctly.
Well, that's partially because they have a very high water content, but you can deep fry squid. Cuttlefish, not so much, but squids, they do serve deep fried squids. Yeah, calamari, that's it. Cool. So I think we are good for today's lecture. Once again, the passcode, if anyone is interested at this point, it is octopus. Where do we turn in? There's nothing to turn in. It's an ungraded assignment, so you just have to kind of go through the motion to do it and verify to yourself that it's working. So there are two types of conversion. You can do a any base to base 10, and then you can do a base 10 to any base. So it's up to you, to decide, how you want to do this. I just want you guys to kind of think about how to code this. That's all. All right. So let me check the direct messages because I got 2 of them. All right. Oh, okay, got it. Oh, okay. I never thought of converting the 310 documents into so that you guys can learn how to do the LaTeX thing. And then the other one. All right. All right. So I'll answer the other one in private, and then getting back to the class channel. Alright, so I think I can safely turn off screen share at this point. Once I turn off screen share, which means the Google Meet is going to end, you guys can go ahead and get started with the lab. I'll be around for the next 2 hours or so that if you guys run into any questions about anything, I can go ahead and answer those questions in Discord. Alright. So I'm going to turn off my Google Meet at this point. Alright, stop presenting first. There we go. And